equation expert tutorials. So today we're going to look at what is known as dimension analysis. So my name's the person who is presenting this is Simko Kenny, Bachelor in Nuclear and Particle Physics. So we're going to look at an introduction to its concepts and applications. So we have to know what dimension analysis is. So dimension analysis is just a method used in physics or engineering to check the consistency of an equation. So what does that mean? So like if you're a mathematician, or as you go further with mathematics, you'll be showing if an equation is consistent. So you can use some concepts from physics to show that the equation is consistent, meaning that the solutions can be found. An equation has solutions. That is the meaning of being consistent. For an example, I can give is, let's say you're given a system of equations. So let's say you have x squared plus y squared is equal to 4. Then also have x plus 4y is equal to 2. Prove that this equation is consistent, which means you should be able to get some values of x, which can be any constant b, a, then you can also find the solution, which is y being equal to what? B. So this is the implication of being consistent. So you have to use dimension analysis. You can use dimension analysis to show that an equation is consistent. There are some equations that you can't find a constant solution. Let's say you have an equation that is just an equation that only has constants. You can show that equation has solutions. You're going to use dimension analysis to show the consistency of that particular equation. Then the other thing is to convert units between systems. So they are what you call the derived quantities. I believe one of my colleagues presented on that. So derived quantities are just quantities that come from basic quantities. So the combination of basic quantity will give you a derived quantity. An example is a force. A force consists of some fundamental quantities, which are fundamental quantities like mass, length, and time. So length, mass, and time, these are we call them fundamental quantities because they cannot further be divided into other quantities. So that's where all other quantities are derived from, and those are what we are calling dimensions. So we are able to come up with a unit for a given quantity. A force is a quantity. So because it is a quantity, it has units. Let's say you don't know the units of force. So how can you come up with the unit of force? You are going to use dimension analysis. An example, as I said earlier, is a force. Force is given by MA. Considering mass, this M, mass is in kg. You already know this because these are basic concepts that I believe you've mastered from your secondary level. You have kg, then you have, acceleration is the velocity, distance over time. So you're going to have meter per second squared. So you should be able to come up with these units from what? Dimension analysis. So you are able to come up with, because since I've talked about dimensions, mass is a dimension. So because it is a dimension, you're able to drive different, you are able to come up with units for different quantities. Because from this dimension, you can come up with a unit for acceleration, force, all these other quantities, or all these derived quantities. So this is what you should know. So from dimensions, we use the same dimension analysis to analyze the units of a physical quantity. Then drive a relationship between quantities. So you can also use this same dimension analysis to drive the relationship between different quantities, like the same force and the other quantities, like an acceleration, velocity, or that. Yeah. So these are some of the use of dimension analysis. As we go further, as we proceed in this chapter, we're going to look at also the limitation, because anything has a limitation. So there is where it starts and where it cannot exceed. So it also have some limitations. So so some basic physical dimensions I've talked about: the length, mass, time, temperature, electric current, amount of substance, which is actually more those who have done chemistry, what amount of substance is, luminance intensity. So we talk about light itself. So you can solve an example from this same knowledge that we've gotten. So like since I think there's one thing that I haven't explained well. So like length, the dimension of length is capital letter L. So length, we'll be using this as the dimension. Then mass, we are going to be using capital letter M. Time, we go to T. So these are dimensions. These are what we call fundamental quantities. So under dimension analysis, our focus is much based on these fundamental quantities, which we are calling dimensions, because that's where all other quantities are derived from. The units, the driving the relationship between all these same quantities. You can come up with an equation from these same dimensions. So you're able to drive an equation from this same dimension. So these are one of the uses. I believe this is very applicable to those who want to do engineering, want to venture into physics. So you can use some of these to analyze your equation, especially if you are in a research field where you want to you are doing some research based on a certain theory. Now you've proved it, but you need to come up with an equation. That equation has to be consistent. So how are you going to show that this equation is consistent? You're going to use some basic knowledge, which is dimension analysis. So those are one of the application of dimension analysis, because this is applied physics. So you can apply this dimension analysis in your research field. Then we can try to drive. So you can show that this equation is valid. How can you show that it's valid? So as I said earlier, there are some limitations. So like for the constant values, dimension analysis does not consider consider the constants. So when you are showing that this equation is dimensionally correct, we eliminate the constants. So this is what we did. So this is basically what we did. So you correct data because period is actually time taken to complete one oscillation. So it's time itself. So I'm going to denote because to say the period is in seconds, so they are just one and the same thing. It's just that a period is a time taken to complete a certain oscillation. If you are dealing with different physical quantities that you are measuring, because each event can take place at a different interval. So the longest interval will be called a period, then in short, that's where you have time. Then we have L, which is actually length. You have gravity. Gravity is an acceleration due to gravity. This is what we're doing in this case. So let me try to show you it here. So to say acceleration. So acceleration is actually meter per second squared. With this in mind, let me do this. With this in mind, to say this is more like you are saying that it's meter over second squared. But mathematically, you are a mathematician, you can write this in that manner, which is just one of the something. But to say second is an SI unit for time. This mass, not mass, this is meter per second, which is actually the distance, is length. It is length that you're talking about. So we're going to have capital it L. Then you have what? T. Then outside you have what? -2. So this is what you are doing here. Then after that, you can substitute those values into the equation. Considering that the constant is dimensionless, we are going to eliminate it. So this is what we did. Okay, let me use a different color just to. So here, this is a constant. This is a constant that we have here. So what you do, you after substituting these values, because you're going to substitute this value there, then this one there, then this one there. So after doing your substitution, this is what you are able to get. This is what we got. Then L is going to cancel with that L. Then there, if you are given an equation, if you have 1 over t to the power -2, you can write this as just you can write this in that manner. So this is what we are doing here. So what we're trying to do is we want to show that this equation is dimensionally correct. In short, what I'm trying to say is, for an equation to be dimensionally correct, the principle of homogeneity has to take place. What do I mean by that? What I mean is the left-hand side, the dimension of the left-hand side should be equal to the dimension of the what? The right-hand side. So those are one of the basic things that you need to know. And the other thing is the principle of heterogeneity, whereby an equation, for it to be not to be dimensionally correct, the left-hand side shouldn't be equal to the right-hand side. So those are one of the principles of of dimensional analysis that you need to know: the principle of homogeneity and the heterogeneity. All this. Yes. So we were able to solve further. Then from that, we are able to get this beautiful equation here. So you can see this is equal to that. So the principle of homogeneity applies here, because the left hand side is equal to the right hand side. So hence we can conclude and say it is dimensionally correct. You've shown that this equation is actually correct. So before you use any equation or any formula in physics, let's say you forgot the formula, but you have some basic concept of what is we call dimension analysis. You can analyze that equation if that equation that you want to use is actually correct. But you that can waste a lot of time. But as you go further practicing, you'll be able to know how to drive this equation. So even this same equation for a period, you can drive it. If you are smart enough, you can actually drive that same formula. Yeah, you can drive this equation. But as we go further, you know how to drive these equations to come up with an equation. So the other thing, the use of dimension analysis, you can use it to drive a formula. Yeah. So how can you drive a formula? So we have a question: find time t to a 4 height h under gravity. So let's say you have you have an object that is falling, so it is moving that direction at a certain height. So there is a certain height we can call h there. So we have the gravity taking place down, because gravity acts downward. It is pulling that object down. So we're going to have the weight, which is actually the force, or mg itself. So we are considering that. So we have this equation. So that's an equation that we're having. So we have t being equal to k h a g b. So this is actually h, then this is g. So you can see this equation. You can come up. We want to drive this equation. So from this equation, we can come up with some dimensions. So dimension, because we are driving the formula. In short, we want to find the value of a and b, so that when we substitute, we'll get what we want. So dimension for t is capital letter t in that manner. Then h is actually length, which is just here. Then let me do this. So it's actually here. Then gravity, I think we've talked about this. This is what we've been mastering all along. So this one we have L, that manner. Then we have t, then -2 there. So taking this into consideration, we can now substitute this. So let me read this properly. So we have t being equal to k, considering that as length. So we have L, that manner. Okay. Then we have so we're going to put these in brackets. So we have L, so we have this is A. Then we have not A, but before we substitute, so before substituting, we are going to go, so we're going to write t -2, then you have this is B. So if you go further with this, then distribute the B there. But since we want to find the formula, our aim is to find the value of A and B. So what you can do here is we can eliminate the constant because it is dimensionless. We can eliminate the K. So what are we going to get? So let me try to remove this part. So we have T, then this is L. So we now distribute the B. So we are going to have L, then you have B, then you have T to the power negative 2B. Because it is multiplication here, L and L, they are multiplying this equation. So here it's more like you have there is one which you can't see, because you know to say any number to raise to power 0 is 1. So if we say L to the power 0 to the right hand side, because it's just one and the same thing, it will still be T. Then you create this equation, you say okay, you can say this is equal to 0. Then we have L, A, then we have L, B. So you can call this as your equation what? Equation 1. Then the other equation is this one for T. So we say T is equal to T negative what? 2B. So you can call this as your equation 2. Considering those equations, because if you are applying the laws of indices, so these basics have been, according to the laws of indices, when you have such things, you can okay, let me do this. Going to solve. I'm just going to continue this, but I'll just use a different color. Okay. So from equation 2. So from equation 2, we can equate this and come up with an equation. So because this is to the power 1, so of 1 is equal to negative 2b. So we can conclude and say here b is equal to negative 1 over 2. So we've gotten one value there. Then what about for A? So what we do here, we know to say this is equal to 0. So from equation 2, from equation 1, we have 0 being equal to, this one was going to be in A, because using the laws of indices, we are going to add that, so we have A plus B. Then from here, you know what your B is. So 0 is equal to A minus 1 over 2. So actually, if you simplify this thing, or this equation, you are going to get A being equal to 1 over 2. So we can see that solutions are A is equal to 1 over 2 and B is equal to negative 1 over 2. Now get these equations and substitute them, because we are deriving the formula from the constants that we are having there. So how do you do that? So you can here using those values for t, so just substitute it, so to be h, because h is 1 over 2 to be 1 over 2, and this is g is negative 1 over 2. You know, this is more like, okay, let me remove this part. So we want to show, to prove this equation. So this is very simple, but if you are not careful, it can become satanic, very hard for you. So at tertiary level, we take everything serious. We don't underrate any question. So this will be k, because you know to say a is 1 over 2, then you know b is negative 1 over 2. So t is equal to, so yeah, you can, you know, if you have, because I know you like x, I don't know why, but you like x, so that's the reason why I'll use x as an example. Negative 1 over 2. This you can write it as 1 over x, 1 over 2. You're not, you know, you're not changing anything there. So that's what I want to do here. So we have h 1 over 2 over g 1 over 2. But remember that 1 over 2, if you have something like this, you can further do, this is more like it's 1 over the root of what? X. That's the implication there. So this is what you're doing even here. So because you have this one means a root and this means a root, it's more like you're having, you know, this will be h over g. This is the implication. So everything is in root. Because I'm saying that because the reason why I'm saying that, so I'm trying to break down these points for easy grasping. So what I mean is, this is actually t. What I mean is, you know, because you are saying that this is same as the root of h over the root of what? G. But this is equal to the root of h over g in of k here. That's the implication. So this is how the formula is going to look like. This is how it is going to so actually this is t. So this is how your formula is going to be. And you know to say this equation is actually the period of a pendulum. And you know to say k, which is a constant, is 2 pi. So which means you've derived that same equation. So you can derive the formula from dimension analysis. Then let's talk about some limitations. Do you have limitations here? No, we talk. Yeah, I think I've already talked about the limitation, such as not recognizing the constant, and the other limitation, I don't know, like they are not here, but the other limitation is does not recognize the exponential function or trigonometry functions. So it does not, you know, recognize those ones. So whenever you are dealing with a trigonometry function, it does not consider. So focus on the dimensions, those that are considered when dealing with the dimension analysis. So those are some of the limitations that you need to know. When you're dealing with trigonometry or exponential function, they are not recognized. Same applies to the constant, like the way we are not recognizing a constant value. Then what are some of the uses of dimension analysis? To ensure the correctness of a formula, so we've showed that this formula is correct. It helps us to drive relationship between variables. I think I've talked about this on the first part, the use of dimension analysis. I think the introduction part of what dimension analysis is. Then useful in unit conversion, important in experimental physics. Yeah, these are one of the uses of dimension, especially if you intend to be a physicist or rather a scientist. You need to, because under experimental physics, so that means you're experimenting, then you come up with a theory. That theory you need some equation, because physics without some equation, I don't think it's physics, because physics is most based on the formulas. So you're going to come up with a formula from dimension analysis and analyze if that formula is what correct. So as a scientist, you ought to know how to analyze data. So you can analyze the equation. There's data analysis. You analyze the data that you are using to do that particular experiment. Then after that, come up with an equation, then analyze if that equation is actually valid from those experiments that we are undertaking. Thank you so much for watching this video. I wish you all the best. In this journey that we've embarked on at tertiary level, we study to understand, not to memorize. So I believe you've learned something. You are going to learn something from this video. Thank you so much.